Before going into the implementation video, let's first look at the transistor models that we are going to use. In this experiment, we are going to use an NMOS and the PMOS transistor. As mentioned in the explanation video, the two transistor models are identical, with the NMOS shown in the left, having a model number ending up with 51, and the PMOS has a model number ending up with 52, shown in the right. The two transistors are manufactured by the same manufacturer, so the pinout is the same, which is the same as shown in the datasheet of the 51 available in the manual. In this experiment, we are going to study the CMOS logic circuits, the CMOS inverter to be specific. To do that, we're going to look at three things: the V input, V output characteristic of our CMOS inverter, the effect of the supply DC voltage VDD on our transfer characteristic, and finally the output drive capability of our CMOS inverter. The CMOS inverter consists of an NMOS and a PMOS with the two drains connected together. The source of the NMOS is connected to the ground. The source of the PMOS is connected to the supply DC voltage, and the two gates are connected together with their inputs. The output is taken from the two drains. For the first part, we're going to see the input-output characteristic of our CMOS inverter. For an ideal inverter, the graph should be somewhat like this, where the two levels of the high and low are distinct. We can identify the high level and the low level distinctively. However, for practicality, we won't have an inverter with this ideal characteristic. The practical characteristic will be somewhat like this. The x-axis will be the input voltage, and the y-axis will be the output voltage. To understand how well is this inverter behaving, we'll look at four voltages. We'll define this voltage to be the V output high. We'll define this voltage to be the V output low, and we'll define this voltage to be V input low, and we'll define this voltage to be V input high. Using these four voltages, we can measure two parameters: the noise margin for the low level and the noise margin for the high level. We'll start by setting our connecting the circuit and setting the DC supply voltage to be 5 volts. If we go here, we'll configure our multimeter to be a DC voltmeter and apply a DC supply voltage from our breadboard and check that the supply voltage is of 5 volts. And we can see that it is almost 5 volts. Going into our circuit, we can see that the top MOSFET is the PMOS and the lower MOSFET is the NMOS. The two drains are connected together, and this is the output is taken from this node, which is the two drains. The source of the NMOS is connected to the ground, you can see here, and the source of the PMOS is connected to the supply voltage. The two gates are connected together, and the input is applied to the two gates. If we apply the DC supply, we'll define our input to be of a triangular wave. Our input will be a triangular wave of frequency 1 kHz. To define a triangular wave in our function generator, we'll select the ramp and set the symmetry to be of 50%. The amplitude will be 10 volts peak to peak, so the maximum will be 5 volts and the minimum will be minus 5 volts. And the frequency, as we said, will be 1 kHz. We will apply our triangular wave, and we can see that this is the output. This is the input and this is the output. We're interested to see the input-output characteristics, so we'd have to use the utility, then go to display, and select the format to be of XY. After selecting the format to be of X and Y, we know that the X-axis is of channel 1, which is the input, and the Y-axis of channel 2, which is the output. We want to measure the 4 voltages mentioned earlier. To do that, we would have to center our characteristic to be in the middle. To do that, we'll just use the position knob and make sure that the vertical position is of 0 volts. So move it slightly until it's 0 volts. And then we'll move the other one to be of 0 volts. Now that the two characteristics are of 0 volts, we'll adjust the scale to be able to read the 4 voltages. So maybe we'll make the scale of 1 volt and 1 volt, or maybe 2 volts. Okay. Now we can see that there are this is what is called the hysteresis, that the curve is not continuous. When it's going one way, the other way is not the same one. So this doesn't affect our result. We're really interested in four voltages. So we know that the step, each step from the horizontal and the vertical is of 2 volts. We can measure the first 2 voltages of V output high and V output low. We can see directly V output low is 0, and V output high is of 2 and almost 5, because each step is 2. So this is 2, 4, and this is in the middle, so it's 5 volts. For the remaining 2 voltages, V input low and V input high, we can measure it from the x-axis, but however, we can see that the graph is somewhere shrinked, so we'll just expand the horizontal divisions to be of 1 volt. So now we know that each horizontal step is of 1 volt, and we can easily measure. This is what is called a V input high. And we can see that it's almost 1 volt or 1.1 volt. For V input low, we can see that it's between the 2 volt and 1 volt, and we can see if we take the middle point, we will consider it to be of 1.5 volt. Using these 4 measured voltages, we can calculate the 2 noise margins. For the noise margin of low, we can calculate it to be of 1.5 volt, and for the noise margin high, we can calculate it to be of 3.9 volts. For part 2, we'll use the same setup, but the only difference is we'll change the supply voltage. We'll adjust the VDD we'll increase it from 5 volts and decrease it and see what happens to the characteristic. So using the same setup, we can see that this is the case of the 5 volts. If we increase the DC supply voltage, we can see that the characteristic is approaching the ideal case. If we go the other way around and decrease VDD, you can slowly see that the characteristic is being distorted. And this is because of the high and low levels are approaching each other. In part 3 of our experiment, we will bring our DC supply voltage back to 5 volts, and we want to study the output drive capability. What this means is that we'll study how the load resistance affects the low level and high level of our inverter. So we will divide this part into 2 cases. The first case is that we're going to fix V input to be of 0 volts. By doing that, we expect that the output voltage should be high. And since we know that our DC supply is 5 volts, our output voltage should be 5 volts. And we will vary our load resistance to see how this output voltage varies from the 5 volts. So the first case, we will apply 0 volts and expect an output voltage of 5 volts. Should this be the case for all the load resistances? We will see that. We will do, in our case, we will do 2 parts. We will consider the load resistance to be of infinity, so we'll keep this open circuit. And then we'll put a resistance between this point and the ground of 10 kilo ohm. And we'll measure the output voltage and measure the output current. We will also do another trial by changing the load resistance to be of 2 kilo ohm. So 3 cases, we'll do open circuit, 10 kilo ohm, and 2 kilo ohm. For the output current, rather than disconnecting this point and connecting an ammeter in series, we will just divide the output voltage by the load resistance. So for the open circuit case, the output current will be 0. And for the 10 kilo ohm and 2 kilo ohm, we will divide the output voltage by the load resistance to find the output current. So the first part of case A, we will connect our input from the 2 gates directly to the ground of 0 volts. And the output is taken from the drain, and the output is taken from the drain, and we'll fix the DC supply voltage to be of 5 volts. We'll configure our multimeter to be of voltmeter, DC voltmeter, and connect its ground terminal directly to the ground of the circuit. If we turn on the DC supply and measure the input DC, we just make sure that it's 5 volts, it's almost 5 volts. To measure the output, we'll just put the red terminal to the drains, and we can see that it's almost 5 volts. The second part of case A, we connected the load resistance to be of 10 kilo ohm. We'll measure the output voltage. You can see that it decreased to 3 volts. We'll do one more trial by changing RL to be of 4.6 kilo ohm. And connect it between the drain, the ground, and we'll measure the output voltage again. You can see that it decreased to 1.5 volts. We'll do one more resistance by decreasing it to be of 2 kilo ohm. And we'll measure the output voltage again. You can see that it decreased to 0.6 volts. For case 2, we're going to change the input voltage to be of 5 volts. Of course, for the inverter, we expect that the output voltage should be 0 volts or close to 0 for all cases. In this case, we're going to connect the load resistance between V output and the DC supply of 5 volts and measure V output versus the ground. Of course, we expect that the voltage output should be 0 or close to 0 for all the cases. We're going to vary the load resistance similar to what we did in case 1. Of course, the first adjustment will be to fix the input voltage to be of the DC supply of 5 volts. So we'll remove it from the ground, connect it to the DC supply. So this is the first adjustment to our circuit. Now we will apply the DC supply, and this is the case of RL equals open circuit, and we can measure V output between this point and the ground. So if we measure it, we can see that's equal to 0 volts. Now we will add a load resistance of 10 kilo ohm between this point and the DC supply. And measure the output voltage. You can see that it increased a little bit to 60 millivolts. Now we'll remove it and decrease it more. So it will be 4.6 kilo ohms. And you can see it decreased more. And we'll do one more case where we decrease it to 2 kilo ohm. You can see it increased even more to 300 millivolts. After measuring all these voltages, we can calculate the currents for the case 1 and case 2. For case 1, we know that the resistance is connected between this point and the ground, so that the output current will simply be V output over the load resistance. However, for the second case, the load resistance was connected between this point and the DC supply, so the output current will not be V output over RL2, but rather will be VDD minus V output over R load 2. So using 5 points and we will calculate 5 currents for each case and plot the V output versus the I output. So to conclude this experiment, in this experiment, we studied the input-output characteristic of our CMOS inverter. We saw how the DC supply affects this input-output characteristic. And finally, we saw how the load resistance or the output is affected by the load, which is what is called as the output drive capabilities.